Hello. So, why should I care about memory management if a computer can do it? That's the basic question of the talk. I will start, the first slide. Why do we have garbage? Well, the problem in computers is that we have finite or limited storage. So we have a limited memory, limited amount of memory. So not like, well, in the real world or somewhere else where we have unlimited storage, which is really bad that we have only limited storage. So we have to care about the storage and who has access to the storage. Actually, we also have different kinds of storage. So we have caches, we have the L1, L2 cache of the CPU. Then we have memory, so RAM and hard drive and network or internet. So we have somehow to care where what is stored. We do it manually, but the history shows that we collect too little, and this leads to memory leaks. Everyone knows that those big programs have to be killed by cron every 5 hours or something like that. Well, on the other hand, if we are too angry and free too often or collect too often, so we call free too often, we get broken programs because we have some dangling pointers around, pointers which don't point anymore to any real memory cell, but they're still in use. That's also the case in double-free bugs. You free too often actually, and you get security vulnerabilities, which is quite bad. Also object-oriented programming. While in object-oriented programming, the memory management, the explicit memory management conflicts with software engineering principles of abstraction and modularity. Because you have to care at any point, well, do I now have to collect that object or can I free it now? So everyone who does C++, is there anyone who does C++ here? Oh, that's for fun or for work? So who does C++ for work and gets money out of it? Oh, that's maybe 20. Who does it in his free time for, well, you don't have other hobbies? Quite much. So somehow it feels wrong to do that memory management in the object-oriented way because, well, you can do it in the deconstructor. Who says, well, that you actually want to call a deconstructor? In my view, object-oriented programming is all about, well, I get some objects and play around with them, and if they are not in scope, they can be removed. But I don't really know when they are in scope and when not, because you can hide objects in anonymous functions or something like that, so show us. There's one slide missing. Well, anyway. I will start over with basic algorithms of garbage collection. You probably, or most of you probably know them. That's, the first, the simplest is reference counting. It's really simple. It's like smart pointers in C++. So you maintain a counter per object where you count the number of references to the object. And each time you reference the object from another object, you increment that. And if it's 0, you can just throw away the object. So basically talking with an analogy of, well, maybe a garage. So you have fully equipped garage and you somehow want to throw away stuff. So in the reference counting way, you go around, write on everything which you need or which is needed by something else you need a number. So 1, 2, 3, and so on. And if you're finished, so you have your basic sets of live objects, so the basic set, so you won't throw away your bike, so you also won't throw away your tools for your bike and so on. And everything which has a number of zeros, so which you don't need anymore, you simply can throw away or burn, whatever. Yeah, it's basically a nice idea. It's really simple, but it's slow. There are better ways to do it. The next algorithm I want to introduce is mark and sweep. Mark and sweep, well, you have two phases. The first is mark, the second is sweep. In the mark phase, you mark all the objects, so your bike, your car, and so on. You don't want to be thrown away. Then you mark every object which is used by the objects you don't want to throw away. So you go to your tools you don't want to throw away. Then you go to your winter tires and don't throw them away, and so on. After you finish marking, so you've gone around and put a sticker on everything you want to keep, or things you want to keep, or things you want to keep, and so on. Yeah, and in the sweep phase, you simply remove all the trash. So it ends up with a contained memory region, or with a contained garage. So you have a lot of garbage in your garage, a lot of free space in your garage, but it is not at one place, but it is parted in where the object you just removed has been. Yeah. The next basic algorithm is mark and compact. It's basically like mark and sweep. So you have also this mark phase and sweep phase, but during sweep you also compact the memory. So you first mark all your stuff, then throw away all the stuff you don't need and put the stuff you need into one edge of your garage or of your memory, so that your memory is not anymore contained, but you have one region of use memory and all the rest is basically not in use. Yeah, then as the fourth basic algorithm, speaking in an analogy as the garage. So you have a garage with a lot of stuff. Then you simply buy a new garage, which is equal size. Go to your old garage, put everything you want to keep in the new garage, and burn the old garage. Yeah. Speaking in computer terms or in memory terms, you get a new equal size memory region. Put all the old objects you need to the new one. Yeah, and free the old memory region. The problem here is that you simply only can use half of your memory. So you have the old memory and the new memory, and the new memory must be equal size to the old memory because you may want to keep everything. Yes, so copying garbage collection is also, well, it has its trade-offs. Yeah, these are basically the 4 basic algorithms which are around, and there's a quite complex space of algorithms in use and garbage collectors in use, and they're basically those 4 algorithms a bit iterated and a bit compacted with some other features. So one of them is generational garbage collection. But the basic idea is most objects die young. So you don't, if you have an old object, so an object which is, well, X minutes old, let's say 5 minutes old, the probability that it will die is really, really low in normal or in common programs. This has been analyzed by Mr. Unger in 1984, back then. So the idea of generational garbage collection is that you have multiple generations, a nursery area, and so on. And you segregate all the objects into the different generations. So each time you allocate an object, it goes to the nursery, and well, you do all those garbage collection, or one of those garbage collection algorithms I just showed to each of the generations. But you don't have to do it for all generations at the same time. So probably you can, well, the old objects won't die that much, so the probability is quite low. So you can collect garbage there much fewer than on the nursery, for example. And the nursery, you probably want to collect the garbage from the nursery once you're low in memory or something like that. So you simply separate your memory again by the age of the memory or the age of the objects and do it separately. Yeah, the next feature, or the next design feature you can choose is whether you want to do incremental garbage collection or non-incremental garbage collection. So normal garbage collection, like I just showed, the 4 algorithms have the big problem that you won't be able to do anything in user space code during garbage collection. So once your garbage collection runs, it should run completely. So the algorithm, the mark and sweep or copying algorithm, should start, do all the marking, all the sweeping, and then done, and afterwards your user space application or your user application runs again. That's basically a bad choice because you have multi-threaded applications and all that nifty stuff, and you don't want to have a stop the world garbage collector. So you don't want to stop everything just because you want to garbage collect. That's, yeah, well, what they used in Smalltalk back in the 1990s. They basically had a garbage collector and they said, well, I need some memory and now stop the world, nothing else goes, I'm collecting garbage. Yeah, incremental garbage collection is basically that you have to care about interleaving the garbage collection code and your user space application code, which is not really trivial. You have a design choice there, once again. That's whether you want to use a read barrier or write barrier. So if you access your memory or the user space application memory in a reading way or in a writing way, you have to notify the garbage collector that the user space program just accessed the memory at region 0x deadbeef writable. Because maybe the garbage collector is just in its mark phase and want to go through the 0x deadbeef in the next stage. So basically, what's the read of write barrier? It's an mprotect on Linux or Unix and a page fault handler. So the garbage collectors install itself as a page fault handler that's miscom zigzag-v. And the user space application can run, and once the garbage collector gets notified that the user space application accesses a memory region which is currently in its mark phase or sweep phase, it can do nifty stuff in the signal handler. Well, as long as you can do nifty stuff in the signal handler, or all that nifty stuff you can do in the signal handler on Unix. Well, and afterwards, yeah, it can just go in. So you can interleave your user space application and the garbage collector, which is quite nice. The problem is that mprotect and the signal handler is quite costly, so you have to pay a lot of trade-off. So during access of a random page, the garbage collector just mprotects it. If you access that from the user space, you have first the signal change to the context change to the signal handler. So the operating system has to change from the user space context to the signal handler, deliver the segmentation fault, and then the garbage collector runs. And then when the garbage collector finished, it switches back to the user land. So you have at least 2 context switches, which was quite bad. Back in the 1980s, the symbolic list machine had this in hardware. So you had a garbage collector or a memory management unit in hardware. So you had read and write barriers in hardware. You didn't need to do it in software, to do a signal handler with it. Okay, next I will come to different implementations which are around for garbage collection. There are basically 2 big implementations which are used a lot. That's BöhmGC, that's Böhm-Demers-Weiser conservative garbage collector for C and C++. It's a conservative garbage collector. So what means conservative? Conservative simply means that it doesn't try to collect as many as it can, but it tries to remain safe. So it doesn't know much about the user space application, or doesn't need to know much about the, just stamp on it, much about the user space application. And it simply goes through and marks and sweeps. So it's a mark and sweep collector. Yet simply replaces the alloc call, the call to alloc, to its own allocation. So it first allocates a region of memory and then delegates all the allocations which it receives to give out parts of the allocated memory. Yeah, and free is simply replaced with a knob, so you don't have to care about free. Yeah, and it marks and sweeps, so you can simply plug it into a C or C++ program if you have memory leaks, or if you have double freeze or whatever in your C or C++ program. You can simply link against Böhm-Weiser GC, and it will stop doing that because it sweeps memory in a safe way, and free is replaced by nothing. the problem of BIMWeiser GC, or what the feature or problem or whatever is, that it is conservative. So it doesn't, it can lead to memory leaks, basically, or it doesn't collect as much as it can. Also, the implementation of it is a big bunch of C files, and well, the basic construct he's using, or they are using, is if-def. So once supported on a new platform or to search through the code, it's quite complicated. I did a FreeBSD Spark 64 port of that project, and yeah, well, it was a lot of if-defs, basically, but most of the codes are if-defs there. So he doesn't have separate source files for different platforms, but he has basically everything in one file, or everything in a bunch of files. Yeah, also BIMGC targets C and C++ applications. Then another system I want to introduce, or I want to talk a bit longer about, but because it's quite nice, is MPS, the memory pool system. It was developed from at Harlequin. They produced a garbage collector for PostScript. So they are basically selling or have a licensee at Global Graphics, which are selling printer drivers. Not for the small printers, for the small office printers, but for big printers. And they have a lot of requirements considering code size and, well, safety. Because if such a printer doesn't have any more memory, or if it has a dangling pointer, it's, well, quite bad and shouldn't do that. So they sat down. That was basically the crew who had done garbage collection at Symbolics back in, well, the 80s. They were sitting down and implementing garbage collection in software in C for general purpose computer. And they've really nice abstractions in their code. So they basically use C, and they have a requirement specification. So they've actually code design and code requirement documentations, and every statement is prefixed and suffixed with, or every function call with about 3 assertions in order to be safe. And the trick is that they built 4 different versions of their garbage collector and define the assertion macro, undefine it, or actually do the assertions, and so on. So you get a really fast garbage collector, which has no assertions at all. And if you encounter any bugs, or if you think you have found bugs in the garbage collector, you can use the debug version and try it, where all the assertions are enabled. So I've used that garbage collector for quite a long time, and I saw multiple times that I found a problem in that garbage collector, and it always led to the user space code which contained the problem. It happens in the garbage collector because the garbage collector is the first who knows that that there is a problem at all, because it sweeps to the memory, and once it finds a pointer to nowhere, it says, oh, I've found a pointer to nowhere. I will simply give up. So the crash most of the time happens in the garbage collector, but the garbage collector isn't guilty at all. So how is MPS designed? MPS has an object-centered, or, well, they have some object orientation with macros in C. It has arenas. Arenas are the large-scale memory layout. So basically on a normal x86 hardware, you will use 1 or 2 arenas most of the time. And then you have pools. Pools are for different garbage collection strategies. And pools are contained in arenas. So you could have, for example, one arena which is equal to the size of your L1 cache, one which is equal to the size of your L2 cache, one which is equal to the size of your memory, and one to your hard drive, and then allocate simply several pools in it. So pool for strings, because strings, you know, well, strings, I have the type string, and I know it contains only characters. Well, and maybe null bytes if you use a strange programming language. And so the garbage collection algorithm doesn't need to go through all the strings and try to find any pointers to somewhere else in order to find live objects, which is a big performance improvement. Well, the problem is that you can have pointers between different pools. So pointer from the weak table pool to the whatever pool. And those pools are most of the time at different pages. So you get there a penalty, but they've tried really hard and they succeeded to keep it really low. The penalty you get for intra-pool links or pointers. So they're really fast, and they know when in one pool they are collecting garbage and what they do in other pools. Yeah, the MPS went open source about 5 years ago, I think in 2001 or 2002. They have sold it to, well, a license to Global Graphics, as I already said, and also to a Swedish firm which is doing the spacing and fitting or the design and layout of all the IKEA furniture, which is a real hard problem because IKEA has a lot of standard furniture such as, well, wood 1.20 meters and that, well, maybe round here and there. And the designer of new furniture simply sits there and clicks in an application. Well, I want to make a table, so I draw here a round ellipse and then, yeah, well, something else. And the tool goes through all the possible furniture they have developed and tries to fit in the standard components which are in use or which are available. Yeah, but MPS hasn't yet adapted to major programming languages. Well, it is open source in a way of if you provide open source or if your program is open source too, then you don't have to pay any fee. And if you make money with your tool using that garbage collector, you have to give money back. So if anyone is interested in that memory pool system more, just ask me. I can talk a lot about it, and it's a really nice system. It's also a nice abstraction of operating systems and CPUs. It's not all in one file, and there's no single if-def, or well, maybe 2 or 3, but it's strictly separated. It runs on Windows, on Mac OS, on Linux, on FreeBSD on nearly everything and on a whole bunch of different platforms. And the source code is at least readable. Well, I'm not a C programmer at all, but it's really nice to read. So you have all those assertions and design documents, and you understand the code, basically. Or you can easily understand the code. Yeah, the next few slides about performance or measurement. But the first note is that you can measure, or what can you measure? So you can measure the boom GC against your C application with explicit memory management. And, well, some shiny news, the boom GC will be slower. But, well, it's not really a fair comparison because boom GC is a conservative garbage collector and he has to sweep through the memory, and your explicit collection doesn't need to. And the algorithms in use by boom GC are not state of the art. And, well, basically memory management and garbage collection is there for programming languages where you don't want to care about freeing some stuff. So, for example, a public example would be Java, because about 120% of this room know Java. Would be that, well, in Java, you don't write any deconstructors or any please free this object stuff, but you simply allocate new ones and you want Java to take care of it. So you can't really measure any Java program with GC and non-GC because you don't have a GC version and a non-GC version of it. So all the performance benchmarks of garbage collection are basically flawed, or you have really to look what they are comparing. And most of the time it's, well, I've written this program in C or C++ and doing explicit memory management, and 2 hours later I've plugged in boom GC and now it's slower. Well, that's not really fair. But I've found at least one paper from Hertz and Berger at Uppsala in 2005, so 2 years ago, not really old. And what they have done is hacking up a Java virtual machine, the JIX RVM, the IBM Java virtual machine, with a tool which traces all the allocation and reachability of objects. So object is at one state allocated. Afterwards, it's reachable until it is no longer reachable, so until it is out of scope or no longer used anymore, anywhere. Then the garbage collector traps in and marks it as dead, so it removes it. And they've used the trace file to implement explicit memory management. So they have a Java source file. They're running it through the Java virtual machine, generating, well, that's runtime information, a runtime trace file. And yeah, well, the run of the application. Then they use the trace file and the source code to integrate the manually memory management, the explicit memory management, and then they are comparing the first version of the program and the explicit version of the program. And the results are, well, quite interesting. At first, you can be as fast with garbage collection as you can be with explicit memory management if you have about 5 times of the heap space. So if you have less heap space, you obviously need to run the garbage collector more often because it has to collect more often, because if you have a heap space of your live objects or equally to your live objects, you can't live with dead objects which are not yet freed. So you have to run it really often. Yeah, well, from time to time, or there are statistics that if you have about 3 times of the memory than needed, it's about 30% slower, or 30% slower than the explicit memory managed stuff. Okay, the next one is that locality, so page level locality, is not kept with garbage collection, or with their implementation of the garbage collection algorithms, which are mark and sweep and copying and all that stuff, and they've done a lot of graphics, and basically it's saying that, yeah, if you run garbage collectors, you are trashing your caches. Well, not really new, or not really, yeah, well, I have expected that, or results like that. So if you have enough RAM, enough memory, you just can use garbage collection and it's all fine. You won't pay any time trade-off. Yeah, in the next few slides I will give some active research topics I've encountered during recent years of reading papers and visiting conferences. One is prediction. So if you use a generational garbage collector, if you could predict when you allocate an object how long it will live, or how long it will probably live, and if you are there most of the time right, you don't pay that many trade-offs. What they are currently looking at are probabilities based on the type of the object, which works quite well. Also on the size of the object. So if you have 200-byte objects, those are, well, most of the time short-lived or whatever. Yeah, but there are also heuristics which keep in mind the top of the stack and go through the stack and look at the types at the stack, and if the types match the currently allocated object, the probability that the object is short-lived is high or long, which is quite interesting, and no one can really explain that. Then real-time garbage collection. So what is real-time anyway? We have hard real-time and soft real-time. The idea of hard real-time is that you can give a deadline, and you can hold the deadline of a specific operation or algorithm. So you don't have any algorithm or function which runs for an unspecified time. Yeah, well, it has been done several times with garbage collection. One example is the Jamaica VM virtual machine. It's a Java implementation, and it has a hard real-time garbage collector, there are only two parameters you have to give. That's the upper bound of live memory. So your upper bound of memory you will ever use, and an upper bound of your allocation rate. Then the compiler simply generates code and inserts some synchronization points at which the garbage collector can run or may run or runs if it needs to run. And an upper bound for the garbage collection time can be given if you have those two parameters. Which is, yeah, well, quite nice. So if you know how much memory you will ever allocate in a specific amount of time, and if you know how much memory you will at all allocate, you can simply use it and give statistics. And if you add more real memory to the system, you get lower rates and all that stuff. Yeah, the second implementation I found is Metronome. Metronome is also done by IBM, and it's integrated to the JIX IBM virtual machine. And they say that the interruptions are down to 1 millisecond, or approximately 1 millisecond. They are using an incremental mark and lazy sweep algorithm. And in order to not have to scan everything multiple times, so the whole memory, when you do one incremental step, they do a snapshot and trace that snapshot. Metronome has been published in 2005 or 2006, and while it works, it is an industrial-grade implementation of Java using the JIX RVM. So hard real-time garbage collection is possible. So the next step, or the next research project out there, is how to do multi-core garbage collection. Well, the basic idea would be I've one core for the actual program, and well, one CPU I've spare actually because my application only uses one or something like that. And that the second core is running the garbage collector. That, well, it would be nice, or it is possible to map the same physical memory to different virtual memory addresses in different modes. So while so the same physical memory can be mapped, for example, read-only in one virtual address space and writable in another address spaces. That's at least possible on Mac OS X, and it could give you the feature that you can run garbage collection on multiprocessors. But it hasn't been, well, I've not seen any piece of software which does that actually. Yeah, and then coming to my last slide, the conclusion should be, or is, if you have enough memory, don't bother collecting memory explicitly or manually, because you can do so much wrong. Don't do it. Okay.